Now, often when we're in here and I talk about molecules and things, I try to either go to Miss Frizzle's classroom, sometimes I ask you to join me there, or I talk about Legos. So I figured this morning that I would actually bring in some Duplos. You guys had this when you were little kids, right? Yep. Supersized Legos. Well, they didn't have these when I was a kid. When I was little, I had to play with Legos, regular-sized Legos. But now they've gone smaller. Isn't it interesting? The smaller you are, the bigger the toys, and then you get bigger, they get smaller. Anyway. So I was just thinking, this morning as Mrs. Baker and I were talking in the study, and she was there reading, and I was preparing some other things for today. And she said, so what are you covering again in chemistry? I said, well, we're still on stoichiometry. And of course, she says, stoichiometry, what does that word mean? Where does it come from? And I said, well, stoikos comes from the Greek word, which means in a line. And we were trying to remember. We both kind of sensed we knew what metry means, like geometry, calorimetry. What does metry mean? And it actually comes from an English word, which means as in steps. So what stoichiometry means, or stoichiometry means, is in a line taken in steps. Now, hopefully you saw that from yesterday, and you've seen this from several modules now. Then we talk about chemistry and write these reaction equations. We write the equation, then we balance the equation, then we relate components within the equation, then we solve. We're doing a line in steps, and hence the name stoichiometry. So I thought this morning we're talking about reactions and making things, and we started talking about this idea of limiting reactants. In other words, as a reaction is taking place, the reaction engine starts, and we have reactants that start reacting to make products. And as long as we have what's required to make the product, it keeps reacting. So again, be thankful you don't live in our home, because Mrs. Baker and I were sitting there and I was saying, how can I, again, talk about stoichiometry in a way that might help people, my students, to understand this a little bit better? And I mentioned to her that she says, well, just explain it to me. I said, well, yesterday I talked about recipe. A lot of times using baking as a way of relating to chemistry is helpful. And I said that, let's say that we have this recipe, and I used the same thing I said with you, cupcakes, that I have a recipe to make cupcakes. And in this recipe, there are lots of ingredients, but let's consider the eggs. Let's say for my recipe to make a dozen cupcakes, it requires 3 eggs. But then I find out that I need not 1 dozen cupcakes, but I need 5 dozen cupcakes. How many cupcakes? 5 dozen, right? How many eggs then do I need to make 5 dozen cupcakes? And being a good baker, she says 15. I said, right. 5 times as much product. I need 5 times as much as every reactant. Well, she said, that's not so difficult. I said, yeah, but now we're talking about limiting reactants. And let's suppose that I don't have 15 eggs. I only have 11. How many cupcakes can I make? A little bit more thinking, right? I need 3 for every dozen. But now I don't have 15 to make 5 dozen. I only have 11. Let's say 11 eggs. How many cupcakes can I make? Well, 11. If I need 3 for a dozen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 3 2/3 dozen. Okay? But let's say that when I went to make these, I thought I was going to make 5 dozen cupcakes, and I brought all the ingredients out and I put it on the counter. I measured everything out and I put all the bags away and I had exactly the ingredients I needed for 5 dozen, but at the end, I realized I was short on eggs. And I decided to make as many cupcakes as I could with the eggs that I had. What would be the result of that? And she said, you would make your 3 2/3 dozen cupcakes, and you would have leftover ingredients, right? Because you're not going to put all the flour in, you're not going to put all the baking soda in, you're not going to put all those other ingredients in. You're only going to put in enough to use up all the eggs. And that's exactly what we're talking about when we're dealing with limiting reactants. In the perfect recipe from great-grandma's cupcake recipe, there's a certain recipe that we're to follow. And we decide, you know what, rather than making the 1 dozen like great-grandma said, we're going to make 5 dozen. But then we can't make 5 dozen because we're short on one of the ingredients. How many can we make? And how much of every other ingredient do we need to use up all those eggs? And if we had surplus, what would be left over? If you would, just going to use that thinking as we deal with limiting reactants. Now, one of the other ways we talk about atoms and molecules and reactions is here, is I ask you to think about Legos. And so, like I said, I brought these Duplos in, supersized Legos. I've got some blue blocks, green blocks, and red blocks. And let's say that we were doing a formation reaction. And we had blue blocks, and we had red blocks, and we had green blocks. Oh, and blue is a homonuclear diatomic. And it reacts to produce a B2RG molecule. Okay? So I could sit here and say, okay, I have a certain amount of blue, a certain amount of green, and a certain amount of red blocks. And I said, okay, if I have, in this case, I have 1, 2, 3, 4, 5, 6 times 2 is 12, but I've got 6 sets of 2 blues, and I have 6 reds and 6 greens. Well, how many B2RGs would I be able to make? 6 of them. So if I were to go through, and hopefully you can see that, do we want somebody to actually go ahead and physically make them? Do you want to make up these molecules? Sure. Here, tag team. You guys put together 6 B2RG molecules, which means we're going to take 2 blues. Let's take a red, 1 red, 1 green. Okay? And there's one of our products. Go ahead and make up 6 of them. Hopefully they're kinesthetic learners, right? Because right now they're getting the opportunity that some of you aren't getting. They're actually getting to touch them. And dropping them, right. Good thing I didn't bring the egg at Legos in, right? Lego yolk all over the ground. We're also seeing how quick they are in efficiency, figuring out, how should we do this? How can we work together to most effectively and efficiently produce the 6 B2RG molecules? There's 2, 3, 4. Thank you, sir. 5 and 6. Okay? So what we've just done is we've taken the exact recipe of 12 blues, 6 reds, and 6 greens, and we've produced 6 blue 2 red greens. Everybody see that? Okay. Now, let's suppose, and I'm not going to break them all down and build them again, but hopefully you can visualize this much. Let's say that rather than having 6 sets of 2 blues, we had 11 blues, right? I'm going to take one of these molecules apart. I'm going to steal one of these blues away. It's no longer there. We're trying to make blue 2 red greens. And we've been able to make 5 of them so far, but because we didn't have 6, we only had 5.5. Kind of messes up our recipe. But notice over here we've got extra reactant that hasn't been used up yet. It's not perfectly matched. Something is limiting the reaction. What do we need in order to make one more product? We could make one more product if only we had what? One more blue. If we had one more blue, we could make one more molecule. But since we don't have that one more blue, the reaction stops. The reaction stopped because we were limited on the amount of blue we had. The reaction stops because it does not have another blue. If, however, I were to add another blue, now the reaction engine can start back up again, and I can go through and form my blue 2 red green, and there I have the 6. Because if I have this exact amount, I can make that exact amount. But if I'm short on something, it shorts my product. Yes. It shorts my product. Yes, ma'am. It shorts my product. Now, if I had, rather than having 12 blues, I had 13 blues, what's going to happen? Leftover blue, right? I'm going to have a leftover blue, and this leftover blue is going to be sitting there just waiting for something to react with. And until it has something to react with, it's just going to sit there, which means I'll have a whole bunch of product, but I'll have one extra blue. In that case, both my red and my green are my limiting. Why? Because I ran out of them. I have plenty of blue. Now, if I were to go and add some more red and green, they would react and form molecules. And then if I had any leftover of anything, whatever I don't have left over is the limiting reactant. It's the one thing that controls how far this reaction engine can run. All right, so in the equations, it's important for us to find out what the limiting reactant is, because when we get to the place where we're adding a specific amount, the engine can only run until one of the reactants is completely used up. And once that reactant is completely used up, it can't run anymore. We'll do a couple examples and look through the book, but that's the idea behind limiting reactant. It stops the reaction engine because it runs out of components from which to build product. And because of that, it controls how much of everything is needed. Just like before, when I talked about the recipe, when I run out of eggs, I don't need any more flour, right? Because I'm making a partial batch. If I happen to find another egg, and it's a good egg, and I add it, I could add some more flour and some more baking soda, whatever proportion is needed for that one egg, and I could up my batch by maybe four cupcakes. But if I were to add it, and this is where it breaks down a little bit, because if you add extra baking soda or extra flour, it's going to change the texture of your cupcake, but you can't do that with a chemical equation. If you add an extra and it doesn't have anything to bond with or pair it with to form the product, it just stays there and waits for something else to show up so that it can react and form the appropriate product. Now, kind of an exception to that, we've used the combustion and incomplete combustion, is the fact that when you burn a carbon-hydrogen-oxygen chain in oxygen, if there's insufficient oxygen, rather than making carbon dioxide, it makes carbon monoxide. But most times, if you're short on one of the reactants, the reaction engine just stops. It doesn't have an alternate molecule that it can produce. Okay? Everybody think they understand that idea, at least? We're going to use a few reaction equations to kind of flesh that out a little bit this morning. Example 8.2 in your book, 3rd edition. Example 8.2 says the antacid tablet Tums has an active ingredient of calcium carbonate, and it neutralizes excess hydrochloric acid in your stomach according to the following reaction. So you have a reaction taking place in your stomach. You know, when you see those commercials for Tums, and you see the actor going like this, going, oh, I need a Tums, like this. What they're actually experiencing is acid in their stomach is burning at their acid, burning the lining of their stomach. Okay? So they're experiencing a burn from the acid that your body's releasing to break down the food. So the reaction is calcium carbonate. When you take a Tums, you are introducing calcium carbonate into the excess acid in your stomach. You are hoping that this reaction takes place because the calcium carbonate, when it mixes with the hydrochloric acid in your stomach, reacts to produce calcium chloride and water and carbon dioxide. So look at this reaction. We've got a calcium carbonate, and it's being added to the hydrochloric acid. This is the stuff that's causing the pain. You have pain because of the acid. But if you add calcium carbonate to that acid, it produces calcium chloride, which is a salt. Okay? Calcium chloride and water and carbon dioxide. Is there anything over here that should bother you? Are you ever afraid to say, whoa, look out, there's carbon dioxide over there? No, we exhale it all the time. We breathe it in and breathe it out all the time. So our bodies, we're comfortable dealing with carbon dioxide and water. Anybody here afraid of water? I mean, like, not like a lot of water, like Niagara Falls water or bottom of the pool water. I'm just saying, oh, look out, there's water over there. We're in water vapor right now. Your skin's not burning because you have water around you. Calcium chloride, like I said, it's a salt, and wouldn't expect you to know a lot of the details about that, but I'll tell you right now that all three of these things are benign. You don't experience pain. There's nothing going taking place here. The hydrochloric acid is burning the lining of your stomach. That's what's causing the pain. Yes, ma'am? No. You ought to be dead. You're 80%, so you would trying to separate yourself from yourself. It wouldn't work. So when we take a Tums, we're adding this reactant, and this reactant is going to react with this reactant and produce things that don't hurt. Things that our body will process, things that we'll exhale, and things that we will either urinate or breathe out as water vapor. That's what happens. Okay? Actually, if you noticed in your book, you're going to find out that urination, the water in urination, is primarily from combustion of fuel. When you burn a carbon-hydrogen-oxygen chain in oxygen, it combusts, and it creates carbon dioxide and water. The carbon dioxide we exhale, the water we urinate. That's kind of why at home, on your heater, the furnace that heats your home, it produces water. You have to have a drain to drain the excess water that's produced from your furnace. A lot of people know that when you use your air conditioning, it condenses water and it falls out. But did you also know that when you burn the fuel in your home for your furnace, it creates carbon dioxide and water? And that water needs to be drained away. I know that very clearly in our home. We purchased it just last year. But we had our furnace become waterlogged because the drain was plugged and the water from combustion backed up and filled up the burning chamber. So we finally drained it. Our burning chamber is full of rust because the water from combustion backed up into the burning chamber. Okay? So we're going to take hydrochloric acid, which is burning our stomach, and add calcium carbonate to it to produce these three products. Now, when we balance the equation, it's 2 hydrochloric acid. Anything else? Yeah. Now it's balanced. 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines, a calcium, 3 carbon, 3. Yes. Now it's balanced. Okay, so now that it's balanced, now that it's a legitimate equation in terms of components, and it's balanced with stoichiometric coefficients, now we can use it for stoichiometry. The question says if, and I'm going to use the method that I taught you yesterday here on the board. Okay? It's a shortcut method, but I still hope you understand what you're doing. It's the same exact thing you're doing as if you did the statements of equality. Same exact thing. But when I read this question, it says if 0.0075 moles of calcium carbonate. Now, here's my calcium carbonate. It says 0.0075 moles is in a tablet. Remember, technique is I'm not going to write it directly below this because I'm saving this place in the future when they tell me grams. They've already given me moles. So I'm going to jump down a little bit, leave a space, 0.0075 moles. If 0.0075 moles of calcium carbonate are in a Tums tablet, how many moles of hydrochloric acid can it neutralize? How many moles? How many moles of hydrochloric acid? Now, recognize, we've been given the number of moles of one of our reactants, and we've been asked to solve for another reactant. You don't have to be given a reactant to solve for a product. In chemistry, whenever we know one of the amounts, and we have a balanced reaction equation, we can solve for any other amount. In kind of the same way we would say, okay, but you have 11 eggs. How much flour and how much baking soda would you need, and how many dozen would you be able to produce? In this case, we have been given one tablet is equal to 0.0075 moles of calcium carbonate. How much hydrochloric acid can we neutralize? And again, in this process, we've been given moles, and we're solving for moles, which means we don't even need the vertical legs of our process. If we had mass, we would convert from mass to moles. And then if we have moles, if we were asked for mass, we would have to move up to mass. We go from moles to mass, right? Let's think of it this way. We go from mass to moles is dividing by the molar mass, correct? So I've got a certain amount of mass, and if I divide by the molar mass, I'll have the number of moles. This problem doesn't ask us to do this step. It's merciful on us. It doesn't give us grams and ask us to compute the molar mass so that we can then compute the moles. It gives us the moles. And in the same way, this question is kind to us in that it asks us for moles. If it didn't ask us for moles, but we could solve for moles, and then if it did ask us for the mass, we would have to know that I'm going to multiply by the molar mass. So those two steps of converting from mass to moles and moles to mass, we're spared from that from this problem because it's giving us moles and asking us to solve for moles. Now, between the two things that I'm solving for, I'm looking inside here to find the relationship based on their stoichiometric coefficients. On this side, I'm looking at calcium carbonate. On this side, I'm looking at hydrochloric acid. What is the relationship according to the balanced equation between calcium carbonate and hydrochloric acid? Correct. It is 1 to 2. It's an implied 1, and over here is the 2. So I'm going to write 1 to 2 here in the box. I've been given, and I'm looking for my unknown, which means I'm moving in this direction, which means I'm going to multiply by what fraction? By 2. By 2. Remember, the procedural step is whatever number I hit first goes into the denominator. So since I'm moving from left to right, I hit the 1 first, it becomes the denominator. My multiple is now 2. So I take this number, 0.0075 moles times 2 produces 0.015 moles of HCl, or it neutralizes. Let me change it with an equal sign. It relates to 0.0075 moles of calcium carbonate relates to 0.015 moles of hydrochloric acid. Okay? So if I had 2 moles of hydrochloric acid, I would add 1 mole of calcium carbonate to neutralize it. And since I have 0.0075 moles of this, I can now neutralize 0.015 moles of this. Remember that in this right here, that little statement of equality right there, with my multiple becoming 2, what that actually is, we're multiplying by 2. In terms of units, this is moles of calcium carbonate, and this is 2 moles of HCl for every 1 mole of calcium carbonate. See, that's the statement of equality we would have written before. We would have written 2 moles, by looking at this, we would have said 1 mole of calcium carbonate reacts with and is, let's see, goes to 2 moles here, yeah, 2 moles of hydrochloric acid. That would have been the statement of equality we would have written, and from that we would have produced the multiplier. That multiplier is right here, using this technique of hit the first, drop it down, go across. All I'm saying is it takes I can neutralize twice as many moles of acid as moles of calcium carbonate that I put in. Once we have this reaction, or this ratio, this 1 to 2 ratio, given any amount of either one of them, I can solve all day long. Now if I said, hey, I'm trying to neutralize a certain number of moles of hydrochloric acid, how much calcium carbonate do I need? I'm going to go this way, and my multiple is going to be 1/2. I need half as much calcium carbonate in terms of moles as I do moles of acid. Remember that these numbers are moles, or if you're talking about individual molecules, they're molecules. These are counts. This is not the same as mass. It doesn't say here that I need twice as many grams. Okay? It's not saying that I can neutralize twice as many grams of hydrochloric acid for every gram of calcium carbonate that I use. It's not grams. It's counts. It's pieces. It's Legos. It's individual things. Okay? In this case, these are molecules. So here's a molecule. I need a whole molecule to react with 2 whole molecules. I need 1 mole of molecules to react to another mole of molecules. And that's why we have these vertical portions. These are translations. Translations from mass to moles and from moles to mass. And both of these molar masses are unique to that molecule that it's underneath. This would be the molar mass of calcium carbonate. And this would be the molar mass of hydrochloric acid. But this step process here, the step process, stoichiometry, stoikos coming from line, metry coming from steps. This line following these steps is stoichiometry. All right? Any questions on example 8.2 here in the book? Yes, ma'am. Yes, we've got an on your own, and we're going to use I think it's the same basic process. So we'll do on your own 8.2 in just a minute, and then we'll walk through it as a class. Okay. But recognize in here that you could do this now with, and they mention this in the book, that 1 mole of calcium carbonate relates to, let's say that we were relating calcium carbonate and calcium chloride, okay? Our ratio would be 1 to 1. Calcium carbonate to water, our ratio would be 1 to 1. Calcium carbonate and carbon dioxide, our ratio would be 1 to 1. See, so given this much of this one reactant, we can now say, I'll require this much of this reactant, and I'll produce this much of this product, and this much of this product, and this much of this product. Given that I have a certain amount of one of the reactants, and everything else is going to follow the perfect recipe, the balanced stoichiometric reaction equation. So with the quantity of just one reactant, we can calculate the needed amounts of all the other substances in the chemical equation. Here's your chance. We're going to do on your own 8.2. I'll write it on the board. Work through it. I'll follow behind you a little bit, giving you a chance to give it your best shot, and either give it your best shot so that you get it and get confidence, or give it your best shot and then learn from what you're doing wrong. Here we go. The first step in a long process that converts iron ore into pure iron involves converting iron ore into iron oxide. That step is accomplished through the following chemical reaction. I'm going to drop the phase indicators. Okay, it's not fundamental to the problem, I don't believe. If it is, I'll go back and add them. So we have 4. Switch. New marker. Tough life of a marker. You fail once, you're done. No grace for markers. All right. The reaction is 4 FeS2 plus 11 O2 react to produce 2 Fe2O3 and 8 SO2. So iron ore and oxygen react to produce iron oxide and, let's see. Okay, so if an iron manufacturer starts with 2,512 moles of iron ore, how many moles of oxygen will be needed to react completely with the iron ore, and how many moles of iron oxide will be made? This is an oxidation problem. See, it's a metal-based compound reacting with oxygen to produce an iron oxide. In this case, it's a rust. This is rusting, and they're actually using this rusting process to separate out this element. Okay? This is the first step of a long process to eventually produce pure iron, pure ferrous, Fe, the Latin name. Okay, so go ahead and set up the problem. Again, I don't want to put too much information on the board because setting it up right is the greatest hurdle. But once you set it up right, then doing the math. Yes, ma'am. I will repeat it. Yep. So here we go one more time. That's the balanced reaction equation. It says if an iron manufacturer starts with 2,512 moles of iron ore, the iron ore is this right here. You have 2,512 moles of this. How many moles of oxygen will be needed? And how many moles of iron oxide will be made? Again, the amount here is 2,512 moles of iron ore. It's about 7 till. I'll give you 2 to 3 minutes head start, and then we'll start working it, okay? I'll pick up my Duplos or whatever while we're waiting. Oh no, I'm making some weird molecule. Hope it doesn't blow up. It's like Tetris for grown-ups. It's not going to work. I see what I did. I forgot I did molecular modification. Here we go. Do the problem. Don't look at me. I'm not all that interesting. I've made a robot molecule. Ah! Mm-hmm. Yeah. Don't let the fact that it's not a nice whole number fool you, because it hardly ever works out to be a nice whole number. You're going to have fractions, which means you're going to have decimals that you need to deal with. Okay. But if you know the process, remember stoichiometry, in a line, now we need to follow the metry, the process, the steps. Follow the steps. Just commit to the steps. First of all, make sure your setup is right, then commit to the steps and just do it. So, I say that we've been given 2,512 moles of ore. I'm going to choose to write my ore, because it's given to me in moles, I'm going to choose to skip a space and bring it down. So 2,512.0 moles. Moles of what? Of that iron ore. I've got 2,512 moles. And I was asked to solve for how many moles of oxygen will be needed. It didn't actually ask me how many grams, it asked me how many moles. And it also asked me how many moles of ferrous oxide, this iron oxide here, will be produced. So I've got two problems that I have to solve in this way. The first one I'm going to solve by going from ore to oxygen, right? What's my relationship here? 4 to 11. Right? Which means my multiple, since I'm going in this direction, is going to be times 11/4. Right? And that's going to give me how many moles? 6,908. (6,908) moles of oxygen are needed in order to react with 2,512 moles of ore based upon this balanced reaction equation. The second part said how many moles of ferrous oxide are going to be produced. Well, it's a two-part problem. Let me go ahead and just extend this down one more just so we can see it, because we're going to use the second equation. We're going to move across this time to relate to the ferrous oxide. But we're stopping here because we've been asked how many moles. Again, we already know that we have 2,512.0 moles of ore. What is my relationship between my ore and my rust? 4 to 2. I can simplify that, but the math will be the same. This would be 2 to 1. It's the same as 4 to 2. If you plug in the math as 4 halves, it's the same as 2. So we have 2,512 moles of ore of a multiple of, when it comes across, hits the 4 first, the 4 goes under, which means I have a multiple of 1/2, right? It would be 2 over 4. Written the way I have it now, 2 over 4, but that's the same as 1/2. 2/4 is the same as 1/2. But if, let's say, there was 4, there's 2, you left it that way, you did the math that way, it's the same answer. It's going to be half of this amount. 2,512 goes 1,256 moles of ferrous oxide. See? They're always going to relate to each other according to this perfect recipe. So given a certain amount of one, how much of the other could you produce? Now, let's suppose that we had 2,512 moles of this, and we had 7,000 moles of oxygen. How much would we produce? If we had the same amount, 2,512 moles of ore, but instead of 11 moles of oxygen, we put in 12, 13, 15, 18, however many moles of oxygen we want. As long as it's 11 or greater, we're not going to make any more ore. Because we're going to, we're not going to make any more iron oxide. Because we're going to run out of the ore, and we're going to have excess oxygen left behind.